If calculus is the study of change, then you could say integration is the study of area. So let's have a look at a few applications of integration that have to do with area. Now, when we integrate a particular function, we can find the area between that function and the x-axis. So any function dx, if I draw my axes and I have some function that looks like this, then the way integration works is I can pick 2 points, A and B, where B is larger than A. So let's say this is A and this is B. And I'll be able to find the area under that curve between the curve and the x-axis. So this orange area here will be the evaluation of this particular integral. Now it's worth noting a couple of things. Sometimes we get used to using integration, but it's not the best possible way to do this. So if I have a line like that, that's a straight line, I might find that I'm much better off using the formula for a triangle, if that's B and that's A. So my width is B minus A, and my height is this. So therefore, the area between this line and the x-axis will be 1/2 times B minus A times H. Much easier to do that than to use integration. But they should come up, or they will come up, with exactly the same answer. In the same way, if I have a shape, again, a straight line, and I'm asked to find the area, for example, between these 2 points, I can divide that up into a rectangle and a triangle and add them together. And in doing so, once I add up the spaces, I can have a much more simple calculation possibly than I would if I was using integration. So the point is, it's always good to see whether you can solve this by geometry and not always integration. Now let's have a look at some kind of an example. If I was trying to find the area between, let's say, a parabola and the x-axis, what I could do is, first of all, I'll draw it. And I think it always helps to draw these sorts of functions. And let's say I have a parabola, something like this. So we'll call this x squared plus 1. Let's try and find the area between the line where x equals 1 and 3. So this space here. And the way I'm going to manage this is I'm going to, first of all, create an expression where I complete this substitution, remembering 1 will be the A point and 3 will be the B point. So my orange shaded area will be between 1 and 3 of x squared plus 1 dx. Now, we're going to integrate this expression, and what we'll find is we get x cubed over 3 plus x plus, remember we have our constant between 3 and 1. But when we do an integration between two terminals, our constant will disappear. And that's because once I expand this expression, these two terminals mean I'll substitute the 3 in the first time and I'll subtract substituting the 1. So for example, what will happen is this 3 up here will take the place of the x, 3 cubed over 3 plus 3 plus c. And then I'll subtract the exact same expression, but with the 1 substituted. So 1 cubed over 3 plus 1 plus c. And what's going to happen is this c here will be added, and then I have a subtraction of the same constant. So when we make a direct integral like this, we can leave off the c. Now, when we make a general integral, we need to make sure we keep our constant present. But in this specific circumstances, our c's will cancel out and we'll end up with a more simplified expression. So now we're going to complete this by using our algebra. 3 cubed over 3 is 3 squared, which is 9 plus 3, don't worry about this constant, minus 1/3 minus 1. And all of that comes to 10 2/3, 12 minus 1 1/3. So that's 10 2/3 square units. Or if you wanted to, you could say that was 32 over 3 square units. So that's how we can use integration between two terminals to find the area under a curve. It's great when you've got a curve like this, but remember, if you've got a geometric shape, like a straight line, triangle, square, rectangle, even a semicircle, you might find it much easier to use geometry to find the area under that circle than to use integration. There's one more case though we need to talk about, and that's when we have this situation where we might have a line or a curve which, let's imagine we have some sort of a line like this, and we want to find the area between the line and the x-axis, here and here. So what happens is we have an area below the x-axis and we have an area above the x-axis. And the way we deal with them is we need to make two separate areas. Now, if I had this equation of this line as being something like y equals x minus 1, then this area here we would know is a triangle that will look like this. My intercept will be at -1, so this distance would be 1, and my x-intercept is also 1. So my area of this triangle equals 1/2 base times height, and that will be 1/2. However, if I found the integral of this function between 0 and -1, and let's do it. Sorry, between 0 and 1 of x minus 1 with respect to x, I will get x squared on 2 minus x between my two terminals, which will be 1/2 minus 1 minus 0 minus 0, which is -1/2. Now you'll notice my area should not be negative. This is obviously a positive area, and the idea of a negative area is a little bit nonsensical. But what's happened here is I end up with this negative sign, and that's because my area is below the x-axis. What this means is when I consider an area below the x-axis, I need to keep in mind that taking the integral is going to give me a negative answer. So I need to take the negative of that. Now there are a couple of ways I can do that, and one of them is to put these lines around my function. Those lines are called modulus lines, and what they do is they tell us that we'll get what's called the absolute value, or whatever number appears in here, we take the positive. The other one is to remember that I can make any area underneath my x-axis, I can say it's negative of the integral because the area is underneath. And if I take that negative, then this becomes a positive, and they're the same. So it's very important to keep in mind that when I'm looking at two areas, especially if one's underneath the curve, that I take them as separate areas, this being area A, this being area B, and when I calculate the total area, it will be the area here plus the area here, and I might have to calculate them separately and then put them together at the end. If you found this or any of my other videos helpful, please subscribe to my channel or like the video. Thanks.